as well as flow through an orifice. Right. So we're gonna first look at the one based on flow through an orifice. Right. I don't know how much of flow through an orifice you remember. If you do remember, we did flow through an orifice in mechanotechnics N4 under hydraulic systems. Right. So this, I just want us to look at this exercise to try and jolt your memory. Right. See how much of what you've studied you actually understand. Right. So we're going to look at this problem. This one is based on flow through an orifice, and then the second one is based on pipeline systems. Right. Reads as follows: 40 millimeter diameter orifice. Just to confirm, you do see my shared screen?
Yes, I do see it.
All right. So reads as follows: a 40 millimeter diameter orifice situated on the bottom side of a tank discharges water at an average rate of 16 cubic meters per hour to the atmosphere. The head of water in the tank is 80 meters above the center line of the orifice, and the actual diameter, so the diameter of the vena contractor is 14 millimeters. Now I did draw somewhat of a sketch here, just to show a visual depiction of what is actually happening, or what the problem statement is telling us. So they said you have an orifice. Here's your orifice. It is 40 millimeter in diameter. Now you get the diameter of the orifice, and then you get the diameter of the vena contractor, right? You still remember that part?
Yes, a little bit.
Right. So in having those two diameters, one we take as the actual diameter, the other one we take as the theoretical diameter. So the diameter of the orifice itself we take as the theoretical diameter, and then the diameter of the vena contractor, right, we take as the actual diameter. Right. Hence here I've written the diameter of the orifice as dt, which stands for theoretical diameter. So that's 0.04. And then the actual diameter is given as actual diameter, which is the diameter of the vena contractor. Hence, I wrote it as dA for actual diameter, which is 0.014 meters. Right, and then we are also given this constant pressure head, right, which is 80 meters. Right, they did say that the head of water in the tank is 80 meters above the center line. Right, so from the center line to the water surface is your constant pressure head, which is 80 meters. Right, that's the one I've labeled as H here. Right, now in flow through an orifice, point 1 and point 2, right, are essentially along the same set of axes. Right, it makes things easier for us in terms of also which pressure head to use, right, because we've already been given this pressure head, right, that is this height h from the water level, which is 80 meters, right, and then of course that you take as the ground. Now we're also given q here, right? They said the average rate is 16 cubic meters per hour, right? Now the standard unit of measurement for the flow rate is cubic meters per second. So obviously you'd have to convert the cubic meters per hour to cubic meters per second, right? And then of course the cubic meters remains the same, so we only have to convert the hours to seconds, right? 1 hour is so 1 hour is 3600 seconds. So there we'd have to say 16 divided by 3600, which is equal to this here. So this is how this came about. Any questions on that one?
No, sir.
Right. So whenever you've been given Q, right, because With measurement of flow, we get essentially two findings. One are theoretical, the other findings are actual. Right. So similarly with the flow rate, we have actual flow rate, so actual Q, which we denote as QA, and then we have QT, which is the theoretical the theoretical flow rate. Right. Now, if it happens that you are given a a flow rate, right? You've been given the flow rate, it means they've already worked out, right, that the actual flow rate is the one that you've been given. So that is to say that if ever um, you are given a quantity and it is not specified if it's theoretical or actual, so you take it as actual. Right? That is why we have taken this Q that you've been given here as our actual our actual flow rate. Right? Is that part clear?
Yes, sir.
Right. So that is all you've been given. Now you can look at questions. Right. So the questions are pretty straightforward. Um, it calculates the coefficient of contraction. Right. So you get what is this? The You get the three coefficients. So one of them is the coefficient of velocity, the other one coefficient of discharge, the other one coefficient of contraction. Right. And the way to calculate the coefficient of contraction is essentially, so we denote it as CC for coefficient of contraction. Right. This one is actually the actual area divided by the theoretical area. Right. Now we know that this is pi over 4 times dA squared divided by pi over 4 times dt squared. And then obviously this and that cancels. That is how this comes about. Right. So you can either use the area or you can simply use the diameters. Right. If you have been given both the diameters, which in this case we have been. Right. So you get to get your coefficient of contraction, you simply use this formula, right? And then in substituting, this is what we get. Any questions there?
No, sir.
All right. I will be sharing a document with you where all of these formulas are outlined, right? And then if
Okay.
you feel like you need further help, I'll also be sharing some videos I recorded on what is this, flow through an orifice.
Yes,
I
please,
just
sir.
Right. I just figured probably this one is going to be easy for you, seeing that you've already done this in N4. But I do understand maybe some of you haven't quite done this in a while. Right. So I will be sharing those videos with you. Yeah.
Okay, sir. Yes, please.
Right. Then 5.1.2 is coefficient of velocity. Right. Now, as far as the coefficient of velocity, right, based on what we've been given, the way you calculate the coefficient of velocity is similar to how you actually calculate the coefficient of contraction as well as the coefficient of discharge in terms of, if you look at the numerator, right, if you look at the coefficient of contraction, the numerator is the actual quantity and then the denominator is the theoretical quantity. So similarly with the coefficient of velocity, right, the numerator will be the actual quantity and then the denominator will be the theoretical quantity. Right. The only difference is that, of course, because this is a coefficient of velocity, right? The quantities have to be in terms of velocity, right? So, meaningly, in having to calculate the coefficient of velocity, the numerator will be the actual velocity, and the denominator will be the theoretical velocity, right? Now, here, having established that, so you know, this is where you're headed. You have to use VA over VT. And the question is, do you have VA? Do you have VT? If you don't, based on what you've been given, are you able to calculate both? Yes, you can. Right. So first, having to calculate what is this? The actual velocity. Saying that you've been given the actual velocity, I mean the actual flow rate. Remember that the general formula for calculating flow rate is the velocity times the area, right? And then it depends if you have QA, right? So if you have QA, then it means this becomes VA and this becomes the actual area, right? So here we've been given the actual flow rate. So we use the actual flow rate to calculate the actual velocity, seeing that we've been given the diameter of the vena contracts, the actual diameter. Right. So then, after having used this formula, you then make VA the subject of the formula. Right. Then you simply substitute here. After having substituted, this is what we get. Any questions there?
No, sir.
All right. So no questions here. All right. So after having calculated VA, now you have to calculate the theoretical velocity. Now I chose to simply, instead of having to calculate this, I simply substituted, instead of VT, I replaced it with its formula. Right. To calculate VT, right, the theoretical velocity, right, the formula for it, it's 2 times G times the constant pressure head, which is this one, right? So instead of having to calculate the theoretical velocity, I simply substituted VT with its formula, right? But of course, you can calculate VT first and then substitute it in this formula, right? Either way, however, whichever approach you choose to take, right, you should
Sorry,
come to,
sir.
yes,
Can you just go back a little bit with your slides? I just want to check something. Okay, just there.
okay,
Okay. No, I'm just making sure about that one that you're removing now currently. For the VT, it's a square root of 2 times G times H.
yeah. So what about us?
Okay. No, I'm just making sure. I thought it's HHG. I'm just getting confused a little bit, but I see now.
Okay, okay,
Yeah.
right. So this is the standard formula for calculating VT. It's the square root of 2GH, right? In the videos, I do show you how we get to this point, right? It is important, I guess, perhaps not that much important, right? Because either way, the formula remains the same, right? But I will be sharing a video where I take you through how I get to this point, right? It's essentially the application of Bernoulli's between point one, which is this point, and point two, which is the vena contractor. Right? If you apply Bernoulli's between those 2 points, essentially this is what you come down to. Now remember that theoretical findings, right? They are based on what is this? Theoretical findings are based on. Okay, this word is slipping my mind now. Right, but what I want to say is theoretical findings are based on systems being 100% efficient, right? Which is never the case, right? Oh yes, this is the word I'm looking for. They are based on ideal circumstances. So ideal circumstances being the system, right? The hydraulic system is 100% efficient, right? Hence, when having to apply Bernoulli's between these 2 points, right, it is on the basis, seeing that we're looking for the theoretical velocity, it is on the basis that this here is an ideal system, meaningly it is 100% efficient. Hence, the velocity that you calculate there is theoretical velocity, right? So by that I mean, in having to say in having calculated the actual velocity, and now the the frictional losses are being taken into account, you'd still apply Bernoulli's between these 2 points, but now bearing in mind that it's no longer an ideal system, or you're no longer looking at it as an ideal system, but you're taking losses into consideration, right? And then in that instance, obviously, you no longer use the theoretical velocity because there's nothing theoretical about the system, right? Instead, you use the actual velocity. Are we
Okay,
still
sir.
right?
Yes, sir.
Right. Um, if you need any further explanations regarding this, like I said, I will be sharing the video where I break this down. Now,
Yeah.
perhaps you can watch the videos maybe even after the assessment, because the assessment is going to be pretty straightforward, right? But what I mean is, for more understanding, perhaps you can watch the videos then. Right? There's still a bit of time today and between today and tomorrow, though, so it is up to you. I will be sharing the videos, nonetheless. Nah.
Okay, sir. Thank you. So the videos you're gonna share, it just explains into detail that is also part of the test that we're gonna be writing on Monday, or should I watch it after the test or what?
You can watch it after the test. For the test,
Yes, sir.
this is more or less everything you're going to need. The question in the assessment will be along these lines, right? So as long as you understand how to calculate your coefficients, right, you should be fine. And then also this one, where you have a pipe system and you are asked to calculate the shock losses, right? I'm gonna jot your memory there as well. Right, so if you are able to attempt this question, right, with an understanding, you should be fine for the assessment.
Okay.
Right. And then after having substituted, we get our CV as 0.729. Now, I always advise you to always round off your answers to three decimal places, right? But I don't care too much about the answers, in a sense that maybe depending on how your approach was, in terms of if you took this approach as me, or if you first calculated VT, right, the answer might look a bit different, right? But like I said, I don't care much about the answer, right? What I look at is the approach. So if your approach is good, right, it doesn't matter if your answer isn't exactly the same as the one on the marking guideline. So don't worry about answers. Sometimes students worry too much about not getting exactly what I got. Doesn't really matter. Nah.
Okay, sir.
Right? As long as you stick to rounding off to three decimal places and you take the correct approach in having to calculate whatever quantity you need to calculate, you should be fine. Right, let's look at 5.1.3. The calculate the coefficient of discharge. So CD as coefficient of discharge, just like the other two coefficients. Coefficient of discharge is the flow rate. So this one would be typically CD is equal to QA. So actual discharge divided by theoretical discharge, right? Now, you're also able to use this formula here, right? And how that formula comes about is, now we know that QA is equal to VA times the actual area, and then the theoretical discharge is equal to theoretical velocity times the theoretical area, right? Now, if you were to rewrite this, right, if you were to rewrite this as simply VA divided by VT times actual area divided by theoretical area. Essentially, if you rewrite this like that, essentially what we get is that VA over VT we know is equal to CV times, and then we know this here is equal to the coefficient of contraction, right? So instead of using this formula, we're able to use this one, right? So whichever one you use will be based on which one is convenient, right? But the point is, this is how we get to this formula here, right? And that is why I used this formula, because in this case it is convenient, seeing that I've already calculated CV, or I've already calculated CV as well as CC. Are we together there?
Yes, it makes sense.
Right. Right. So that's the formula I used, and then I substituted what I got at the top, and this is what I got. So CD is 0,09. Now, one of the ways you can tell, or maybe you can um, one of the ways you can tell if your coefficients are correct or not is the coefficients are always less than 1. So if it happens that you calculate any one of the coefficients and they happen to be more than 1, it means something is off there. Right? They will always be less than 1. Do you get what I'm saying?
Can you just repeat that again, please?
Right. So look at all of our all of our coefficients. So the coefficient of discharge,
Mhm.
the one of contraction, and the one of velocity. Right. If you look at all of them are less than 1 in magnitude
Mhm.
value. Right. And that is always the case. Right. Your coefficient will always be less than 1. Always have to be. So I'm saying if it happens that you calculate any one of the coefficients and you happen to get a value that is more than 1, then it means you did something wrong somewhere, or maybe you didn't do anything wrong, but the given information is incorrect. Either way, it, it gives you a reason to pause and check your work or verify your work.
Okay.
Right? So your coefficients, all of them, all three of them, are always less than 1. Right?
Mhm.
Right. Then we look at 5.1.4, the head loss due to fluid resistance at the orifice hole. Right. You see, now we are, the question is based on real life applications um, where frictional losses have to be taken into account. Right. With frictional losses, you get major frictional losses and then you get minor frictional losses. Right. So things like shock losses, those are minor frictional losses. Right. The major head loss essentially is the, what is this, HF, the one we refer to as HF. Right. It's the one where we either use Darcy or Chase's formula to calculate. Right. That one we refer to as the major head loss. All losses though are frictional essentially. It's just that others um, are small losses, hence we refer to them as minor losses. And then you have the one that contributes to the most losses, which is the frictional head loss, HF. Right. So with this question, calculate the head loss due to fluid resistance at the orifice hole. Right. Now they want us to take into account what is this? The frictional head loss. Right. Now there are two ways in which you can calculate this. Both ways. Um, First, looking at this one, right? The way we come to this equation is through the application again of Bernoulli's between point 1 and point 2. The only difference between when we apply Bernoulli's between the 2 points when having to derive the formula for calculating the theoretical velocity is that with having to derive this formula, right, we apply Bernoulli's between the two same points, right, so point 1 and point 2, right, but looking at it from an ideal perspective, so not taking losses into account, right? But for the one we are doing now, we are still going to apply Bernoulli's between point 1 and point 2, but the difference is that now we are taking losses into account, right? Hence, the velocity that you use, right, is no longer a theoretical velocity, right, but instead the actual velocity, right? So when having to apply Bernoulli's between the 2 points, right, we come up to the fact that HF is actually equal to the constant pressure head, right? So the constant pressure head still being the 80, right? The 80 meters in this case, right? Minus V squared over 2G, right? Again, if you're interested in knowing exactly how we come to this, right? It is in the videos I'm going to send you guys, right? So you either use this or you can use this formula this side, right? I'll also show you how we derive this one. So this one we derive from this formula, right? I do show you on the videos how this comes about if that is what you're interested in. But either way, you can use either this formula or this formula to calculate the frictional head loss. Any questions there?
No, sir.
All right. So then we substitute the constant pressure here is 80. Right, we calculated the actual velocity is 28,869. Substitute that G is 9,81 for fluid mechanics, and this is what we get. So you can either use this or you can use this. Again, don't worry about the answers not being exactly the same. Right? What matters is the approach. Any questions on this one?
I just wanted to ask, the answers are not the same, but I understand what you're saying, sir.
Yeah. Right. Right. So let's look at 5.2 quickly. So they say because the diameter of a pipe suddenly increases, the velocity of flow changes from 10 to 6 meters per second. Then calculate the shock head loss under these conditions and the pressure rise under these conditions. Right, so I have drawn here a schematic illustration of the problem at hand. Right, so they said that the diameter of the pipe increases from did they tell us? Actually, they didn't tell us. They just said the diameter of the pipe suddenly increases. Right. So the diameter of the pipe suddenly increases. So meaning point 1, or the first part of the pipe is much smaller than the second part of the pipe. Right. And then we are told that the flow velocity is 10 meters here, and then it is 6 meters, right, at this point. And then first question is to calculate the shock head loss under these conditions. Right, now, as far as the shock head loss, this is simply the formula that you use. Right, shock head loss is equal to, that's the difference in velocities, so V1 minus V2, all squared divided by 2G. Right, that is how you calculate shock losses. Right, and then if you substitute, seeing that we are given both V1 and V2, right, we get the shock loss as 0,815 meters. Now, if you look at the magnitude of this shock loss is 0,815. Right, so would you say that this is a major shock loss or a minor shock loss? is would you say this is a minor loss or a major loss?
I would say it's a minor loss, sir.
Exactly. So all minor losses, right, will be say around this value. You can easily tell the difference between minor losses and major, the major head loss. All right. So that is how you calculate your shock loss. And then they want us to calculate the pressure rise. Right. So the pressure rise will be the difference in pressure between the 2 points. Right. Now, this here is how essentially you do that. Now, one of the reasons why I've included the schematic illustration is so that you are able to understand if the water is accelerating or if the water is decelerating, and how that is going to impact how we look at the pressure at point 1 relative to the pressure at point 2. Now, if you look at the velocities, right, of point 1 and point 2, right, clearly the water is what is accelerating or decelerating here.
Decelerating, sir.
Right, so because it's decelerating, that is why A is in the negative direction. Right, so remember, if you look at direction in terms of the Cartesian plane, take that as positive, that's negative, that's negative. So if you look at this from a horizontal perspective, it is a horizontal pipe. Right, it means positive is on this side, negative is on this side. So which means if the water is accelerating, it means the direction of acceleration is pointing in this direction. Right, now you have F1, which is essentially the force that pushes the water in this direction, and then we have F2, which is the the frictional force, right, that the water is subjected to along the pipe walls. So in terms of which force is greater between F1 and F2, right, you have to look at the direction of acceleration. So based on the direction of acceleration, it means F2 is going to be greater than F1, seeing that this is the force that is going in the same direction as acceleration. That's just dynamics 101. Right. So having established that, then that means that if F2 is greater than F1, it also then means P2 is greater than P1. Any questions on that one?
No, sir.
Right. Right. So after having established that, then you simply apply Bernoulli's between the 2 points. Right. Now, remember that the shock loss has been considered here. So we are also going to consider the shock loss in having to apply Bernoulli's as well. Right. So applied Bernoulli's used this variation of Bernoulli's equation, where each term is in terms of pascals, because we are looking for the change in pressure. So it's just much easier to use this variation of Bernoulli's. Otherwise, you can use any variation of Bernoulli's that you are comfortable with. All right. So in applying Bernoulli's, you say P1 plus this is equal to essentially the second part of the pipe, but also taking into shock losses into account. Right. And then all I did was after having established that P2 is greater than P1, so to get the difference, essentially it's going to be P2 minus P1. So all I did was solve for, or make P2 minus P1 the subject of the formula. So essentially took this that side and took everything else that side. Right. So I took P1 to this side and it became negative, and then took everything on this side. So this and this took it on that side, and it became negative. Are we still together there?
I'm a little bit confused, but I just wanted to ask a question. So, when the losses is taken into account, do you add it or subtract it? Because
So you add it on the second part of the pipe, right? Because losses will have accumulated. Remember here, point one is this one, right? The shock loss
mm-hmm.
happens at this point, right?
Okay,
Where the pipe changes the diameter. That is where shock losses happen. So we
okay,
cannot.
yes, I get it.
You see what I'm saying? You cannot take into account losses at this point. You can only take into account losses after the fluid has traveled to the pipe up to the second point. So at the second point, that is when the fluid has been subjected to losses, not at point one.
Okay,
You see what I'm saying there?
yes, sir.
Yes. Hence, you add it on the second part of the pipe. That is why this is added here. Are we still together?
Yes, sir.
Right. So what I was saying here is that, remember, we established that P2 is greater than P1, right?
Mm-hmm.
Right. And what are we looking for here? We're looking for the pressure rise under these conditions. So the pressure rise is essentially the change in pressure. That is why it is important that you establish which between P1 and P2 is greater. After having established that, then you will know how you will get the rise in pressure. Right. So after having established that P2 is greater than P1, so to get the rise or the change in pressure, we have to get P2 minus P1. So after having written our Bernoulli's expression, we then make P2 minus P1 the subject of the formula. So to make that the subject of the formula, it means P1 must come on this side. Right. So if P1 comes on this side, we will get P2 minus P1. You get that part.
Mm-hmm. Yes, I do.
Hence, this is what we get. And then obviously we'll have to take these two terms on the other side. And when we do that, this term becomes negative and this one becomes negative. That is why V2 squared here is negative, and that is why rho GHS is negative as well.
Mm-hmm.
Right, so you get that part as well now.
Yes, sir.
Right, right. Once that is done, now you don't necessarily have to take this approach. I just find this approach much easier to do. But of course, from this point, you can simply just substitute your values, right, and then um, work things out from that point. Right, I just prefer doing things this way, right, but you don't necessarily have to take the same approach, right? And then you substitute here. In substituting, the rho is the rho of water, it's the density of water. Saying that we haven't been given um, the value of the density of water, we assume it is 1000. That is where this comes from. The 0.5 is this half here. And then we're given V1 as 10 and V2 as 6. Rho and G, we already know. Then HS, we calculated here. And then if you calculate, or if you punch all of this in your calculators, this is what we get. Which again, right, depending on your approach, will be more or less the same as this. It doesn't have to be exactly the same. Any questions there?
No question, sir.
Right. So that is how you will approach such problems. On the test, you are going to get an exercise that requires the same understanding. Right. That's what I'm saying. Um, for flow through an orifice, if you have to remind yourselves, you can watch my videos after the assessment. right, to get a proper breakdown of all the formulas, right, in preparation for the exam. Right, in preparation for the exam, we will have a couple of sessions where we look at past exam questions. Right, we'll take one of the past exam questions and we'll attempt questions together. Right, so now obviously you cannot finish a whole question paper in one session, so maybe we'll split it into, say, 2, maybe 3 sessions, whatever works for us. Yeah.
Okay, so no problem.
Right. So now let's look at this pipeline systems problem. Right. It's pretty simple as well. I just want to highlight this part here essentially, that we do know that if you have a pipeline that either has 2 pipes that are joined in series, or that has a tapered pipe, so a pipe that has 2 different sets of diameters. Like for instance, this one, the diameter here is quite smaller than the diameter on this side. So that is what a tapered pipe is. For such cases, right, we know that the Q, so the flow rate, is the same, right? So Q1 essentially is equal to Q2, right? So I want to highlight how we look at pipes that are not quite connected in series, right? So pipes that are connected, let's say in parallel, how that affects the flow rate, right? So before we get into that, let's first look at the statement, right? And it reads as follows: a company pipeline network system is used to deliver diesel oil with a density of 920 kilograms per cubic meters. Excuse me. To 4 diesel oil substations. Right. The 4 substation pipelines are connected and fed from a single main pipeline of 225 millimeter diameter. Right. So essentially, you have a main pipe that is feeding 4 other pipes. Right. So the main pipe is 0.225 in diameter, and the diesel oil was recorded as flowing at an average velocity of 2.285 meters per second along the main pipeline. So the velocity on the main pipeline is 2.285 meters per second. Right. Now they say 2 of the 4 pipelines are identical in size and have unknown specifications. Right. So I drew a schematic illustration of this problem. Right. We are told here that you have a main pipe is feeding 4 pipes. Now 2 of the 4 pipes are identical. Right. So these here we are going to take as the identical pipes, of which we do not have the specifications thereof. Right. So meaningly we are not aware of the diameter of the 2 pipes, nor do we have the velocity or flow rate through these pipes. Right. Then they say there is a 70 millimeter diameter pipeline in which the diesel oil is flowing at a velocity of 5.235 meters per second. Right. So this would be this pipe in this case. So this I take as my 0.07 meter pipeline. Right. And we are also given the flow velocity in this pipeline, which is 5.235 meters per second. And then the other pipeline is 105 millimeter in diameter. So that would be this pipe. So I color coded the pipes so that it is much easier to understand. Right. So this pipe is the other pipe that is 0,105 in 0,105 meters in diameter. Then they say the flow velocity in the 70 millimeter diameter pipeline, right? So essentially, this one, the flow velocity of the 70 millimeter diameter pipe is 1,5 times the velocity in the 105 millimeter diameter pipeline. So essentially, mathematically, this is what they mean, right? Which essentially, therefore, means that, remember here, we already have the velocity of the flow velocity of the fluid or of the oil through the 70 millimeter diameter pipeline, right? Are you still with me?
It's a lot to take in, but I'm with you, sir.
Okay, right. So we've already, remember, we already are given the the flow velocity of the oil in this pipeline, right? You are told here that there is a 70 meter diameter pipeline in which the diesel oil is flowing at a velocity of 5,235. So we already have the velocity here, right, of oil in this pipeline. And then now we are given a ratio, right, a velocity ratio between between the two pipes. So the 70 millimeter diameter pipe as well as the 105, the 105 millimeter diameter pipe. Right, you are told that the velocity, the flow velocity in the 70 millimeter diameter pipeline, which is this, so the velocity of this one is 1,5 times the velocity of this one. So that is where this comes from mathematically.
Okay.
Are we still together now?
Yes, sir.
Right. Now I'm saying that having been given this velocity ratio, right, between the two pipes, essentially we will use it to calculate the velocity of the oil through the 105 millimeter diameter pipe because we've already been given the velocity of the oil in the 70 millimeter diameter pipe. Are you with me there? Hello.
Yes, sir. You can continue.
So I was asking you if you understood that part,
Yes, sir. I understand that part.
right? So which means it only makes sense to express this velocity ratio in terms of the velocity of the oil through the 105 millimeter diameter pipe. So that is why I then took this and make V105 the subject of the formula. And then in doing so, I found that uh, the velocity of the oil through this pipe, the 105 diameter pipe, is equal to 0,667 velocity of the 70 millimeter diameter pipe. Right.
Yes, sir.
Now, questions. Determine the following. The total volumetric flow rate of the diesel oil flowing along the main pipeline in liters per second. Right, so pretty straightforward. Right, we have everything we need for the main pipeline to be able to calculate the flow rate of the main pipeline. Right, but before we do that, I want us to understand that seeing that the pipes here are essentially not connected in series but essentially in parallel, right? And this here being the main pipeline, or this pipe being the one that is feeding the other four pipes, it means that we can take the the flow rate in the main pipe as our total flow rate, right? And our total flow rate, which I've denoted as Q main here, will be equal to the flow rate here plus the flow rate here plus the flow rate in these two pipes. Right, so this one I named as Q identical. Right, remember that we are told that of the four pipes, two of them are identical. So meaning that they have the two of these pipes have the same diameter. Because they have the same diameter, it means they will have the same velocity as well. Having the same velocity and diameter means that they will have the same flow rate. Right. So that is where this comes from. That the Q here is actually equal to this Q, or the what is this? The so the Q main is equal to the sum of the flow rate in each of the four pipes. Right, that is where this comes from. Do you get that part?
Yes, sir, I understand.
Right. So in having to calculate the total volumetric flow rate, so we know that this here is the pipe that feeds the other pipelines. So essentially, we take this as our total volumetric what is this, flow rate, right? So essentially, them asking us based on how I've denoted the Q's here. Right? Remember, I've denoted this one as Q main. It means seeing that they want us to calculate the total flow rate. It means they want us to calculate Q main. Now, you don't necessarily have to denote everything the same as me, right? This just made sense to me, right? But you don't have to denote everything the same as me, right? So Q main, we know is equal to the area and velocity, of which you have both. Right? So area of the main pipe times the velocity of the main pipe, right? And this is the formula for a round pipe. And then you simply substitute because we've already been given the diameter, which is 0.225 meters, and then we're also given the velocity, right, of the oil in the main pipe, right? And this is what we get in terms of cubic meters per second. Now, they did specify here that they want us to leave our answers in liters per second, right? That is why in converting this to liters per second, right, you simply multiply this by 1,000. Right, you simply multiply this by 1,000, and then this is what we get: 90,853 liters per second.
So when I multiply it, I get on the dot 91. So how is that a bit different?
Okay, let's see what I did here. So I said pi over 4 times 0.225 squared times 2,285. Right, so I get 0,09085338692. So I don't know how you, or perhaps did you calculate the area first and then rounded the area to 3 decimal places?
Yeah, I think I did that, sir.
Yeah, so that's why you got zero. That's why the answer is a bit different. But like I said, doesn't matter much as long as the approach is correct.
Okay.
Right. But yeah, that is how you essentially um, convert from cubic meters per second to liters per second. Right. Now we look at 4.2.2, the mass flow rate of the diesel oil flowing along the main pipeline, right, in tons per minute. So they want us to leave our answers in tons per minute. Now, the mass flow rate, right? The mass flow rate, how we denote mass flow rate is with this M here. So m dot, it's a mass flow rate. So m dot, it's a mass flow rate because it's not just kgs, but it's kgs per second. So the standard unit of measurement for mass flow rate is kilograms per second. Right? And the way you calculate mass flow rate, excuse me, I've got terrible flu. So mass flow rate will be the density of the fluid times Q. Right, excuse me. Right, so that is how you calculate the mass flow rate. Right, and in terms of how the how the dimensions work out, we know the density is kilograms per cubic meters, and then Q is cubic meters per second. Right, so we know this, and that cancels, and that is how this becomes kilograms per second, or that is how the dimensions work, or that is how they cancel each other out in having to get kilograms per second. We together there?
Yes, sir.
All right. So in having to calculate the mass flow rate of the oil flowing along the main pipeline, right, so we know that mass flow rate, we know how to denote it as m dot. So I'll just call it m dot main for perspective. And then we know to calculate a mass flow rate, it's rho times Q. And then because this is for the main pipeline, that is why I call this Q main. All right, so you've already calculated Q main here. All right, so remember that in having to substitute here, you can only substitute your quantities in its standard unit of measurement. So we know that we had to leave our answers in liters per second, but that doesn't necessarily mean that we have to use the answers in liters per second. But you always use your answers based on its standard units of measurement, and the standard unit of measurement for flow rate is cubic meters per second. So that is why I substituted the 0,091 here. Are we clear there?
Yes, sir. If they did not specify that we have to give it in liters per second and we leave it as such, is it not? Is it fine? Because I can't see clearly the question that you just showed there.
Right. So the question here is they said in liters per second, but
Okay.
if they do not specify which SI unit to use, then you always leave it in the standard unit of measurement.
Okay.
Right. Right. So the rho here was given as 920 kilograms per cubic meters. Right. Density of oil, and then Q main we calculated. Right. So that's 0,091, and then this is what we get. Right. But we get the mass flow rates in its standard units of measurement, which is kilograms per second. Now, going back to the question, you see here they said in tons per minute. Do you see that?
Yes, sir.
Right. So because they want us to leave our answers in tons per minute, it means that now we have to convert this to tons per minute. Right. And then in converting this to tons per minute, we know that 1 ton is equal to 1,000 kilograms. Right. So which means one kilogram is equal to 1 over 1,000 tons. Right. That is where this comes from. So to convert the kilograms to tons, right, you have to replace the kgs with 1 over 1000, which is where this comes from. Do you see what I did here?
Yes, sir.
Right. And then um, in terms of converting the seconds to minutes, right, we know 1 minute is equal to 60 seconds, which means 1 second is equal to 1 over 60. What is this? Minutes. So to get rid of seconds and replace it with minutes, we have to substitute it with 1 over 60 minutes, which means essentially you have 83,72, right, over, what is this, over, okay, oh, right, over, so this is going to be the 1000, because remember, this is actually times 1 over 1000, right? That is to convert from kilograms to tons. Get that part, right?
Yes, sir.
And then remember that this whole thing is over seconds. So this is over. Then converting from seconds to minutes, you replace the seconds with the 1 over 60. So here you have 1 over 60. So mathematically, right, we know that we can say times 60 here and then times 60 there, hence that cancels, and then mathematically, then this becomes over 1000, then of course the times 60 there. Do you see what I did there?
Yes, sir. I see.
Right, so that is where this comes from. Right, right, so that is where this comes from. And then of course, as you punch that in your calculators, this is what we get. And then of course now it has been converted from kilograms to seconds to, kilograms per second to tons per minute. Any questions there?
No questions, sir.
Right. 4.2.3, calculate the volumetric flow rate of the diesel oil flowing in the 105 millimeter diameter section in liters per second. So now they want us to calculate the Q for this pipeline, so the 105. Right. Now here we have the diameter, but we don't have the velocity of the oil through this pipeline. But we do have this velocity ratio that we were given for these two pipes, right? So because we have the velocity of this one, it means we can get the velocity of that. Once you get the velocity of this one, now you can calculate the Q, seeing that you have the area, right? That is why here, to calculate the Q for the 105 pipe, right, you simply say the area, right, the area of that pipe, which is this one, times the velocity of that pipe. Okay. Right? And then, of course, this you are able to express in terms of that ratio that we worked out. So remember this ratio, right?
Yeah, yes, I remember that one.
Yes. So you simply substitute this velocity with that ratio, right? And then the diameter is given, it's 105, which is 0.15. And then the velocity of the 70 millimeter diameter pipe is given, remember, as the 5,235 meters per second. And that is where this comes from. Right. Now, I didn't show the conversion here, but remember they said that we must leave our answers in liters per second. Right. So whatever answer you get here, you simply multiply that by 1,000, essentially. And this is what you get, the 30,235 liters per second. Are you getting more or less the same thing?
I'm quickly busy calculating it, sir.
All right.
Yes, sir, got the same answer.
All right. So that is how you do that. So as you see here, it's just a matter of knowing how to play around with the flow rate in terms of if the pipes are connected in series or in parallel. All right. Otherwise, we already know the standard formula of calculating Q. All right. So I just wanted to highlight here with this exercise. I wanted to highlight right this understanding that if the pipes are connected in parallel, how the approach is in terms of the total flow rate, or in terms of how to calculate the total flow rate in terms of um, the flow rate in each of the pipes that are connected to the main pipe. All right. Right. So this is what we get. And then we look at 4.2.4. They say you must calculate the diesel oil volumetric flow rates in each of the two identical pipelines. So they want us to calculate the Q in each of these identical pipes. Right. Now at this point, we have Q main, right?
Mm-hmm.
The Q70 we haven't calculated, but we can get it because we have both the diameter as well as the velocity through this pipeline. We have just calculated Q105. So essentially, we can use this expression to calculate the Q identical. Do you see what I'm saying here? Hello.
Yes, sir.
Right. So they've asked us to also leave our answers for this one in liters per second. So if you look at the flow rates that we've calculated, all of them essentially we have expressed in liters per second. So in calculating Q identical, right, using this expression, you can simply substitute each of your Qs in liters per second, right, so that you don't have to convert at the end of your solution. Do you see what I'm saying here?
Mm. Okay, I see, yes, sir.
Right. So first thing is, you first calculate the Q through the 70 millimeter diameter pipe. You have the diameter there, it's 0.07. We are also given the velocity there, which is 5.235. And then in liters per second, this is what we get. Just confirm if you get the same thing more or less.
Yes, sir, got the same.
All right. And then now, after having calculated this Q, essentially in this expression, we have all the Qs except the one we are looking for. All right.
Mhm.
So all the idea was simply make this the subjects of the formula, right, and then substituted all of the Qs in terms of liters per second, and this is the magnitude I got. Are you getting the same thing?
I'm still busy, sir.
All right.
Yes, sir, I got the same.
All right. All right. So the approach is clear to you. The approach we took here in having to calculate the Q identical.
Yes, sir.
All right. So you see how drawing a sketch, even if you don't draw it on the actual scripts, your answer scripts, you can draw it even on the question paper. But how it eliminates a lot of our problems here. Right? And then also writing down this expression, right? It helps quite a bit. Right? That is why in the lower levels, in fact, in all levels, but that is why specifically in the lower levels, we teach you um, to make use of free body diagrams. Those free body diagrams, um, they they tend to break down the problem uh, quite well. Hence, when having to do the the solutions for whatever that they're looking for, right? Some of the answers you've already identified on your free body diagram, essentially. Right. Any questions here?
No, sir.
Right. So last question, 4.2.5. Calculate the diameter of each of the two identical pipelines in millimeters if each pipeline has a flow velocity of 4,756. Right. This one is pretty straightforward as well. Remember, at this point, we've calculated the Q in each pipe. Now they want us to calculate the diameter of the two identical pipes, given that the flow velocity in each of the pipes is, or in each of the two pipes, is 4,756. Right. So there, you simply use standard formula for calculating Q. Right. We already have this. This is what we're looking for, and then this is given. So all I did there was simply make the diameter the subject of the formula, right? Which in doing so, so in making the diameter ID, in making the diameter the subject of the formula, essentially this then becomes Q identical, right? Q identical divided by pi over 4 times the V for identical, right? And then all I did here was, instead of writing this as a fraction, I simply multiplied by 4 both sides. Hence, this then becomes pi here, and this is multiplied by 4. Right, and then of course, in substituting, Q identical is this here. Remember, this was expressed in liters per second, right? But in
Mm-hmm.
use here, it has to be in cubic meters per second. You must use it in its standard units of measurement, right? So, in converting from liters per second to cubic meters per second, you then divide this by 1,000. That is where this comes from. Are we together there?
Mm-hmm. Yes, sir.
Right, and then that times 4, which is this one, divided by the pi, which is this one, times the velocity that is given, which is the 7, the 4,756 meters per second. Right, now we are told to leave this in millimeters, the diameter of each of the two identical pipelines in millimeters. So because we've been asked to leave our answers in millimeters, so the answer you get here, right, will be in meters, right? So you simply multiply that by 1,000, and you should get more or less what I got here, which will then be in millimeters. So just calculate there and see if you get the same thing.
Yes, I got 73.60316. Yeah, I got the same.
Okay, right, and that is how you do that one. Now, of course, you don't necessarily have to take this approach. Right, you can simply take whatever mathematical approach you're comfortable with here. Either way, you're going to get to more or less the same thing. Any questions?
No, sir.
All right. These are the two exercises I wanted to highlight essentially, because I remember I thought about sending you for the videos for flow through an orifice, but then I thought of time, and then I was like, I'll just go through one or two exercises based on what is this fluid in motion. Right, so that is flow through an orifice, and then this one is fluid in motion. Right, so I thought I'd just do one or two, which will at least prepare you for the assessment, and then this one as well. Right, what is this pipeline systems? I thought that maybe you have never done a problem like this one, where you have to think about how the pipes are connected. Are they connected in series or in parallel? Then how does that affect the total flow rates in terms of how you calculate it? So I thought let's do a problem based on that, so that you can have an understanding of how you would approach such a problem. Right? And then in terms of you understanding, say, flow through an orifice in much details, I'm going to share videos with you for that.
Okay.
Right. If there are no questions, we can end the session here. Right. You guys still remember the assessment plan for the second test?
Yes, sir, I wrote it down, and which was that it will include the hydraulic system, the fluid in motion, the pipeline system, the flow through orifice, and then the flow measurement using instruments, and then the properties of fluids. Is it
Yes.
still the same?
Yes. Still the same. Yeah. After having done the two exercises that we did today, or the two questions that we did today, yeah, you should be fine.
Okay, I just want to recap, sir. The ones that we just did now, as you specified, it was the ones with that includes the pipe systems and the fluid in motion, correct?
So the first one we did was flow through an orifice,
Mhm.
and then the second one
Mhm.
in that first question is fluid in motion,
Mhm.
and then the second question was pipeline systems.
Okay. So you meaning the third question actually, sir?
Sorry,
Are you repeated in saying is the second question?
second question. Yes. Remember,
Okay.
we did three exercises, but two of them were under the same question.
Oh yes, yes, yes. I understand. Yeah.
So that's why I'm saying first question, second question.
Okay.
Yeah. I will share the video in the group, and then I'll also send um, those work exercises in the group as well for you to refer
Okay, sir.
um, as and when you need. Right. There's another one that I want us to do on pipeline systems, but we'll do it after the second assessment.
Okay, sir.
Yeah. Is there anything else?
No, sir. I had a question, but I forgot where I wrote it down. It was regarding one of the question papers that you given to us that we have to work out.
Yeah.
Yeah,
It's
but
fine.
I can't find it now.
When you do remember, just shoot me a text.
Okay,
If
so I'll do so.
it's something I have to explain, I'll just do a short video and I'll send it to you.
Okay, okay, sir.
All right.
When will when will this class be posted, sir?
Right now,
The recording of
I'll,
the class. Okay,
I'll download it and right now. So as soon as we end this session, I will download the session, then upload it on my channel, and have the link available to you once it's been uploaded. Uploaded.
okay, sir. Thank you.
All right. Study well over the weekend, and all the best with your assessments.